Everything you've ever seen, every star, every planet, every galaxy, every atom in your body represents less than 5% of the universe. The other 95% is invisible, untouchable, and undetected. Yet without it, galaxies would fly apart and the universe itself would tear at the seams. And right now, something with the mass of tens of thousands of galaxies is dragging us through space at about 2 million kilometers per hour toward a destination we cannot see. In the 1930s, Fritz Zwicky looked at the Norma Cluster and realized the math did not add up. Galaxies were moving too fast to stay bound by the gravity of visible matter. Decades later, Vera Rubin measured galaxy rotation speeds and found outer stars were moving as fast as inner ones, demanding vast, unseen halos around galaxies. That is when dark matter went from fringe theory to fundamental problem. Today, the picture is wild. About 5% is regular matter, about 27% is dark matter, and roughly 68% is something even stranger called dark energy. We know dark matter does not emit light, barely interacts except through gravity, forms massive halos, and acted as scaffolding so the first galaxies could form. Simulations without dark matter fail to build the universe we see. With it, you get the cosmic web. But what is it? Scientists hunted WIMPs with ultra-sensitive detectors like Xenon 1T and Lux and found nothing so far, wounding the once dominant idea. They probe axions with ADMX, chase sterile neutrinos, and even consider primordial black holes, which likely cannot make up all the dark matter. Modified gravity ideas like MOND explain some galaxy motions but stumble on clusters, lensing, and the cosmic microwave background. The bullet cluster becomes a smoking gun. Hot gas slowed down in a cluster collision, but most of the mass sailed through, revealed by gravitational lensing. Exactly what dark matter should do. Quick question to spark the comments. If you had to bet today, what do you think dark matter is? WIMPs, axions, primordial black holes, modified gravity, or something else entirely, and why? Drop your take below and let's compare reasoning. Dark matter pulls, but dark energy pushes. In 1998, two teams using type Ia supernovae discovered the expansion of the universe is accelerating. That shock earned a Nobel Prize in 2011 and forced us to confront dark energy, which appears uniform, does not dilute as space expands, exerts negative pressure, and might be a property of space itself. Einstein's cosmological constant, the vacuum energy of empty space, could explain it, but quantum calculations overshoot observations by a mind-bending 10 to the power of 120. Dubbed the worst prediction in physics. Alternatives include quintessence, modified gravity, and even scenarios where acceleration tears everything apart in a big rip. Meanwhile, the Hubble tension looms. Early universe and late universe measurements of expansion disagree by about 9%, hinting at new physics or subtle errors. Missions like Euclid, the Vera Rubin Observatory, and DESI are mapping the cosmos to pin this down. Now the ride gets personal. You are moving through space at about 600 kilometers per second because our local group is plunging toward the Great Attractor, a gravitational focal region roughly 200 million light-years away, hiding behind the Milky Way's Zone of Avoidance. X-ray and radio observations revealed clusters like Norma, but the real picture is bigger. We belong to the Laniakea Supercluster, where flow lines converge into the Great Attractor like water down a drain. And even that is being tugged toward the colossal Shapley Concentration, home to over 8,000 galaxies and the mass of tens of thousands of Milky Ways. The universe also has the opposite of these mass hubs, voids. The Boötes Void spans about 330 million light-years and holds only about 60 galaxies, where you would expect roughly 2,000. Its few galaxies are odd, often small and star-forming, and the emptiness stretches our models. Ideas range from natural evolution of structure and earlier dark energy dominance to unusually large early fluctuations. Even speculative bubble collisions from inflation. Voids likely contain diffuse dark matter that never lit up with stars. And then there is the universe's baby picture, the cosmic microwave background. In 2004, a cold spot about 10 degrees across, roughly 70 microkelvin cooler, stood out in WMAP data and was later confirmed by Planck. It spans about 1.8 billion light-years and is statistically unlikely on standard expectations. A gigantic supervoid in Eridanus might account for part of it, but not all. Other ideas include a statistical fluke, topological defects, or exotic early universe scenarios. Add in the axis of evil, hemispheric asymmetry, and missing large-scale power, and cosmologists are left wondering what we are missing. If you are loving these mind-benders, hit subscribe so you do not miss the next deep dive. Here is the truth bomb. We understand about 5% of the universe. The rest is dark matter, dark energy, and mysteries we are only beginning to map. New detectors, colliders, and telescopes are coming online, and every unanswered question is a roadmap to discovery. Which of these cosmic mysteries keeps you up at night?